Hello there, AP Environmental Science class. Welcome to part one of my lecture on Chapter 19, Air Pollution and Ozone Depletion. All right, once again, I will break this chapter down into two lectures. There's 63 slides, I believe. So again, I'll do low 30s, both part one and in part two. So once again, here starts part one, Chapter 19, Air Pollution and Ozone Depletion. All right, looking at a core case study, as we normally start off our lectures with. This is Los Angeles and its air pollution. In the 1950s, Los Angeles air was among the dirtiest in the world. Industrial emissions, along with motor vehicle emissions, along with the fact that in Los Angeles, they get a lot of inversions, and we'll talk about what an inversion is in a couple of slides. But basically, it's when cold air is on the bottom and warm air is on the top, and that actually caps the atmosphere and keeps the pollutants down near the surface, potentially for many days. I don't know if you ever heard of something called the June gloom in Southern California. If you have friends out there or family, you know that in June, July, and August, it stays cloudy a lot, and usually the air is not the cleanest, and that's because of the inversions that's set up. And again, we'll talk more about that in just a bit. Public protest over the smog in the 50s and 60s led to, in 1970, Congress passing the Clean Air Act, which mandated pollution control measures, and this resulted in dramatic improvements in air qualities in Los Angeles. Right now, revisiting, they have the lowest pollution levels since 1999. The largest source of pollutants still are parts of Los Angeles and Long Beach, where a lot of ships burn diesel fuel. And again, pollutant is trapped by the mountain ranges, and that builds up those thermal inversions. So again, while the air is cleaner in Los Angeles than it was back in the 50s, still especially in the months of June and July, you can get that inversion to set up, that smog to basically hang around for a couple of days, couple of weeks, and that obviously can lead to issues if you have any respiratory ailments or things like that. So, what is the nature of the atmosphere, right? So we're talking about air pollution and ozone depletion in this chapter. So we have to understand the atmosphere. So there are basically four zones of the atmosphere: the troposphere, stratosphere, mesosphere, and thermosphere. We're just going to be really concerned with the troposphere and the stratosphere. So the troposphere is the layer of the atmosphere that basically we are in here. It is the lowest level. Starts at the surface, and it supports life. Most of the weather that occurs in the troposphere. Above the troposphere, we have something called the stratosphere, and what is important about the stratosphere is it contains the protective ozone layer, which protects us from the harmful UV radiation coming from the sun. Without that ozone layer, there would be no life here on planet Earth. So thank you for that. And again, the stratosphere is where that ozone layer is. All right, so again, the atmosphere, what is it? Just some terms. It's a thin blanket of gas, right, that surround the Earth. Density is the number of gas molecules per unit air of volume. It decreases with higher altitude, right? The further up you go, the less air there is, so the less density or the less air density you have. Pressure, right? Atmospheric pressure is how much pressure in the atmosphere is pushing down on you. Force per unit area of a column of air. And again, it decreases with higher altitude, right? If you go up, there's less air up there to push down on you, so the atmospheric pressure decreases. This is why if you go high in the mountains, sometimes it's hard to breathe because there's actually less air up there than there is down here at the surface. So this is what we're looking at. Again, here are those four zones I talked about. What's interesting is the zones are broken up by the temperature trend. So the troposphere, temperature decreases with height. In the stratosphere, it increases with height, and that's because the ozone layer is absorbing the ultraviolet radiation, which is heating up the atmosphere in the stratosphere. So believe it or not, the temperature actually increases as you go up. Back to the mesosphere now, the temperature decreases again, and then up in the thermosphere, the temperature will actually increase with height as you get out into space. So again, just have a general understanding of the atmosphere here and the temperature trends in each layer. If you just memorize the troposphere with decreasing temperature, everything else is just a pattern, right? Decrease, increase, decrease, increase. So it should be fairly easy for you to remember. All right, air movement and chemicals in the troposphere affect Earth's weather and climate. So again, the troposphere is the layer of the atmosphere down here near the surface, the one that we interact with, and 75 to 80% of Earth's air mass, right, is in the troposphere, right, because we have the most air down here as that air pressure is pushing down on us. Again, it's closest to the surface. Its composition of gases, pretty much 78% nitrogen, 21% oxygen, and then the rest, a little bit as a bunch of all these little other gases in the atmosphere. But again, the main gases are nitrogen and oxygen. Rising and falling air currents and greenhouse gases play a major role in weather and climate. What are our greenhouse gases? Water. Believe it or not, water is the number one greenhouse gas. It's the most efficient at trapping infrared radiation trying to leave the Earth. The reason we don't talk about water vapor as much is because it's not anthropomorphic, meaning it is not being created by humans. The amount of water vapor in the air is the amount of water vapor in the air, right? It's not necessarily changing, or at least around the planet, right? We don't lose water, gain water, things like that. So we don't talk about water vapor when we talk about greenhouse gases because, again, it's not anthropomorphic or being created by humans. Carbon dioxide, methane, and nitrous oxide, obviously different stories, right? While they are produced naturally, we are putting more of those three pollutants into the atmosphere, and that is producing the runaway greenhouse effect. I do want to point out a greenhouse effect is good. If we didn't have a greenhouse effect on this planet, our average temperature would be 0 degrees Fahrenheit. There would be no life. We would be an icebox planet. But however, because we have these greenhouse gases, the infrared radiation, the heat that comes out, gets trapped, sent back down to Earth, and keeps us nice and warm like a greenhouse. The problem is we're producing a runaway greenhouse effect because we are putting too much carbon dioxide, methane, and nitrous oxide into the atmosphere, and that then produces global warming. So I want you to know greenhouse effect is not bad. It's only bad because we humans are increasing it, or again, putting it on steroids, as I like to call it, making it more intense because we're adding too much, again, carbon dioxide, methane, and nitrous oxide into the atmosphere. The stratosphere is, again, the layer of the atmosphere above the troposphere, usually 17 to 48 kilometers above Earth's surface. Similar composition to the troposphere, except there's very little water vapor up there. That's why most of the weather occurs in the troposphere, because you need water vapor to produce weather, clouds, rain, snow, things like that. And the ozone layer is in the stratosphere. That's where your ozone, O3, has your highest concentration. Again, what does the ozone layer do? Filters 95% of the harmful ultraviolet radiation coming to us from the sun, and it allows life to exist on land. Again, without that ozone layer, there would be no life on land on this planet because the ultraviolet radiation would cause cancer in cells, and that would basically not allow evolution to have occurred. And again, we wouldn't be sitting here talking about this. So thank goodness for that ozone layer in the stratosphere. All right, so what are the major outdoor air pollution problems? All right, so a couple here. One is industrial smog, and the other is photochemical smog. Industrial smog is caused primarily by burning coal, like industry. Photochemical smog is caused by the emissions from motor vehicles, some other industrial facilities, and power plants. All right, those are the two main types. So air pollution comes from natural, right, of course, and human sources. So air pollution is the presence of chemicals in the atmosphere which have a concentration high enough to harm organisms, ecosystems, human-made materials, or alter climate. So what are some natural sources of air pollution? Wind-blown dust, right? You got a dust storm in the desert. That dust gets blown up into the atmosphere. That's pollution. Pollutants from wildfires or volcanic eruptions. Again, you could be talking about carbon dioxide, methane, other types of toxic gases that are released into the atmosphere. Again, but these are natural sources. Volatile organics released by plants, also natural sources for air pollution. However, as we've learned in this class, the Earth can handle natural disruptions, right? Because it has ecosystem services that clean up. Okay, so the atmosphere has its own way to clean itself up from those natural air pollutants. Unfortunately, now we're going to talk about human sources and what happens with most in this class, right? When we bog down the natural processes by adding more pollution, now we reduce or even eliminate the ability of Earth's natural resources, those ecosystem services, to actually clean out the atmosphere. So where is our air pollution human sources coming from? Mostly industrialized and urban areas. We have stationary sources like power plants and industrial facilities, and we have mobile sources like our cars. So two types of pollutants. There are primary pollutants, with our pollutants emitted directly into the air, and then secondary pollutants are formed from the reactions of primary pollutants. So it's kind of a double whammy. Not only are these primary pollutants polluting the atmosphere, but then they combine together to produce more pollution, known as secondary pollution. So again, double whammy here. And that's what we're looking at in this picture. Now look, I would have a general idea. I have seen some test questions talk about primary and secondary pollutants, all right? So I would take a look at this, understand, have to memory some of the primary, some of the secondary, right? So carbon monoxide, carbon dioxide, right? Here's your methane, okay? These are your primary pollutants, but then when they combine with other elements in the atmosphere, they produce secondary pollutants. Believe it or not, ozone is a pollutant near the surface. In the stratosphere, we like it. It blocks us. It blocks the ultraviolet radiation. But here at the surface, ozone is actually causes respiratory ailments. So it's actually a pollutant, a secondary pollutant, right? We have sulfuric acid, okay, which is also a secondary pollutant. All right, that doesn't come out of the smokestacks, right, or the volcanoes, or coming out of your car. But as you these primary pollutants work with other elements, other particles in the atmosphere, you get sulfuric acid, et cetera, et cetera. All right. So again, just understand some of the primary and secondary. And if you have additional questions, make sure to come see me and ask me about them. All right. So obviously, we're talking about this all because air pollution obviously has harmful effects. So air pollutants flow north to form Arctic haze. So believe it or not, in the Arctic, where there is no pollutants because no one really lives up there, all the pollutants from the south actually flow up to the north because our winds go from kind of hot to cold. So it moves all those pollutants to the north and produces a haze in the Arctic of pollution. Since the 1970s, outdoor air quality has improved in the more developed countries because we put laws or in there enacted to clean up the air. But unfortunately, in some of our lesser developed countries, they don't have those laws. Fine particles can get lodged in the lungs, right? Those are particles of air pollution. That contributes to cancer, asthma, heart attack, and stroke. Outdoor air pollution kills 1.4 million people per year in China. And over 500,000 people in India, again, are killed each year because of outdoor air pollution, giving them cancer or asthma or heart attacks or stroke. So again, something to think about. And obviously, we need to clean this up as much as we can. All right, so here are your major outdoor air pollutants. Again, we looked at that chart. Here are the ones you really need to concentrate on. So we have the carbon oxides, right? Carbon monoxide, carbon dioxide, right? Those are primary pollutants we spoke about. Nitrogen oxides and nitric acid, right? This leads to acid deposition, which is acid rain. They also play a role in photochemical smog. We'll talk about that more in a second. And again, your sulfur dioxide and sulfuric acid, which are those secondary pollutants, reduce visibility and can aggravate those breathing problems. We have particulates, which are just basically suspended particulate matter, basically suspended little particles of pollution in the air that you can breathe in and then get lodged in your lungs. Obviously, ozone in the stratosphere is good. Down here at the surface is bad, can cause coughing and breathing problems. And then we have something called VOCs, volatile organic compounds like methane and benzene, dry cleaning fluids, and various components of gasolines and plastics. When they release their fumes into the air, that is also a major source of outdoor air pollution. So, here are some chemical reactions, right, that we speak about to form these major air pollutants, right? So carbon monoxide is basically two carbon, and that oxygen comes together to form 2CO, right? Here's your carbon dioxide. Here's your nitric oxide. Here's your nitrogen dioxide. Here's your sulfur dioxide. Again, these are your major air pollutants and the chemical reactions that cause those pollutants. We definitely have a general idea of these as well. While you may not have to memorize the chemical reactions, you may have to work with them a little bit on any tests coming up. And of course, on the big AP test coming up later this spring. So again, definitely take a look at this chart in detail. And if you have questions, please come and see me. This is some of the results of the air pollution, right? So this is a statue in Rome that has obviously been polluted. Sulfuric acid and other air pollutants has damaged the statue. What you'll notice here, this whiter piece has been actually restored. So this is actually newer, even though you can even see some of the acid or sulfuric acid, right, beginning to affect it as well. But look at the rest of the statue, right? This is what it used to look all white. Now it's all black. And that's, again, sulfuric acid coming down, acid rain because of air pollution. Again, basically damaging these statues, and you can see damage like this all over the place, unfortunately, because of that acid deposition, or otherwise known as acid rain. All right, case study to talk about here. Lead is also a highly toxic pollutant. We don't talk about it as much these days, but when I was your age, lead was a big issue. Not only lead paint, but lead in gasoline. So lead is in air, water, soil, plants, and animals. It does not break down in the environment. Impacts human health. Children are most vulnerable, can cause death, brain damage, and paralysis. Lead exposure for adults and children working in those e-waste recycling, right? We spoke about that in a previous chapter. One of the issues, the toxic chemicals in there, in that electronic waste, is the lead. So here are just some solutions and prevention and control of our lead poisoning. Again, this was a much bigger issue back in my day, but obviously still an issue today. So prevention, replace lead pipes and plumbing fixtures containing lead. Phase out leaded gasoline worldwide, which in this country you can't find that anymore. Phase out waste incineration, because that can send the lead into the air. Ban the use of lead solder. Ban the use of lead in computers and TVs, right? Just basically ban it. Control, remove leaded paint and lead dust from older houses and apartments. Again, that was a big push back in the 1980s and 1990s when I was your age. Sharply reduce lead emissions from those incinerators. Remove lead from TV sets, computers before you put them in landfills, right? Test blood for lead by age 1 and test for lead in existing ceramic ware used to serve food. You could get lead that way as well. So once again, we know these charts. Try to remember a few of them if you need it on an FRQ. All right, coal. So we're going to talk about industrial smog, then we'll talk about photochemical smog. When it comes to industrial smog, burning coal is the main cause of that. All right. Unfortunately, coal, as we spoke about in a previous chapter, while it is a very high net energy yield type of way to get energy, it's the dirtiest around, right? So not only do you have sulfur dioxide, sulfuric acid, you have suspended solid particles that make up this industrial smog. So you can imagine it's not good to breathe. The combustion of coal and oil forms carbon monoxide, carbon dioxide, and soot. Soot is another way to say suspended solid particles. It's common in industrial urbanized areas like China, India, the Ukraine. Beijing's air quality among the world's worst. If you go out into the Midwest here, we have some coal plants as well. Obviously, we control our pollution a little better here in the United States, but still, any coal plant is putting out this industrial smog, or at least these chemicals that then produce industrial smog. So once again, here is a simplified model of how pollutants are formed when coal is burned. And again, the result is industrial smog. So again, I would have a general idea of this, right? So sulfur in coal and oil, carbon in coal and oil. The carbon goes right into carbon monoxide, carbon dioxide, and that's soot, right? Sulfur goes into sulfur dioxide, right? Then sulfur trioxide when some oxygen is involved. Here's your primary. Now here are your secondary pollutants, right? Oxygen in the atmosphere combines with sulfur dioxide to produce sulfur trioxide. Water vapor then combines with that to produce your sulfuric acid. Ammonia in the atmosphere then combines with that to produce ammonium sulfate. Again, secondary pollutants, right? Once you get past the sulfur dioxide here, because again, you have other elements or other chemicals or other compounds in the atmosphere that are then merging with these pollutants to form even more pollutants. So again, general idea here, right? understand it, all right, this is how coal produces industrial smog. Another very simplified model here. This is how pollutants make up photochemical smog. Now, photochemical smog is more from car emissions, not necessarily from coal coming from industrial plants, right? So nitrogen in your fossil fuel, right, gets released, and now it starts combining with those other elements to produce nitric oxide, nitrogen dioxide, right? UV radiation comes in here to produce more nitric oxide, and oxygen atom forms with oxygen to produce the ozone. And then you have these PANs and other pollutants that end up merging with the volatile organic compounds. So again, very simplified model here of how this industrial smog is created. But what you can tell, and what the point is, that even though we're only putting out maybe that bad nitrogen or the carbon dioxide, because of all the other compounds in the atmosphere, they then form with the pollutants to produce even more pollutants. So again, it's kind of like a runaway system here. We put one pollutant in the atmosphere that then produces 3 or 4 other secondary pollutants. So again, this is the problem, and this is why we have to try to curb as much of this industrial smog, right, photochemical smog, from happening by trying to eliminate or at least mitigate the amount of pollution that is being released by these sources. So sunlight plus cars equals photochemical smog, right? Photochemical smog formed under the influence of sun's UV radiation, right? You have your VOCs and some nitrogen oxide and heat, plus sunlight yields ground level ozone and other photochemical oxidants, aldehydes, and again, other secondary pollutants. So that's your photochemical smog, right? Basically, you need the sun, you need those VOCs, and that's basically what we get, especially when we see those, our cars emitting it, and then again, getting trapped under an inversion, which we'll talk about in just a second, and that then increases the photochemical smog, keeps it around, and that obviously can lead to major issues. So, factors affecting outdoor air pollution, right? Factors that help reduce it. Gravity allows particles to settle, right? So again, that's a natural ecosystem service. Rain and snow, believe it or not, cleans out the atmosphere. Again, an ecosystem service. Salty sea spray from the ocean will clean out the atmosphere. Wind, very similar to running water in a stream. Wind will turn over the atmosphere and again allow it to clean itself. And natural chemicals reactions actually remove some pollutants. So again, these are the factors that help reduce it, the natural capital, our ecosystem services. But again, because we're overloading our atmosphere with those pollutants, unfortunately, these ways that that Earth provides us or helps us, again, they get overwhelmed and unfortunately can't clean the atmosphere as much. Because factors that increase outdoor air pollution include urban buildings, hills and mountains, high temperatures, again, those VOC emissions from trees and plants, the grasshopper effect, and that temperature inversion, which is where warm air above cool air prevents mixing, and that then traps the pollutants. The grasshopper effect is the effect of moving the pollution from one part of the world to another. So, like basically moving it up to the Arctic haze, that increases your air pollution effects, the movement of air around the Earth. So, this is what we talk about when we talk about an inversion. Again, normally in the troposphere, right, we talked about how temperature decreases with height. As you know, cold air is more dense than warm air. So if you have cold air above warm air, the cold air sinks, the warm air rises, and you get a circulation in the troposphere, which basically cleans it out and keeps it nice and fresh. However, an inversion will set up, especially near mountain ranges and cold water like you get in Los Angeles, like you get in China, where colder air is near the surface and warmer air is up top. Well, the colder air sinks, the warmer air rises, and what that means is you basically get an area where there's no mixing in the atmosphere. And so now you're releasing chemicals from either coal plants or from your automobile cars, and it's just getting trapped in the troposphere because the troposphere isn't overturning itself, because the warm air is on top and the cold air is on bottom, and that's nice and stable. And so you get a situation where your smog, your chemicals, your pollutants are trapped under this inversion. And again, in some parts of the world, this could last for weeks or months on end. And again, obviously very, very bad, especially if you have respiratory ailments, because you're basically breathing in these pollutants for days. And again, the atmosphere is not able to cleanse itself because of this inversion that has set up. Again, big issues in cities like Los Angeles and Shanghai. All right, acid deposition. This is acid rain. Why is it a problem? Well, it's caused mainly by coal-burning power plants and motor vehicle emissions. Threatens human health, aquatic life, and ecosystems, forests, and also human-built structures like that statue I showed you about. I showed you from Rome. So, human-generated NOx and SOx in the atmosphere, right? Wet deposition is acid rain, snow, fog, or acid cloud vapor. Dry deposition would just be acidic particles just falling out of the sky. And again, these substances remain in the atmosphere for 2 to 14 days, and again, could cause issues. So here we have, again, natural capital degradation from acid rain. So where do we have our nitric oxide goes up from our cars, right? Or sulfur dioxide and nitric oxide from our power plants. It transforms into sulfuric acid and nitric acid. Again, there's your secondary pollutant. The wind then blows it somewhere else, where again it gets mixed in with rain or snow and then falls as precipitation onto the land, and then that obviously can begin killing trees and aquatic life because you're increasing the pH. You're actually, decreasing the pH, right? You're increasing the acidity, and once you do that, plants and animals can't really live. So this was a big issue again back in my day, back in the 80s and 90s in the Adirondacks, actually, which are the mountain range here in northern New York. There was a lot of issues with acid rain because all of our industrial plants are located in Ohio, in the Midwest, Ohio and Indiana, Illinois, excuse me. And if you know the prevailing winds out of the Southwest, so all that photochemical smog and industrial smog that was created in the Midwest blew to the Northeast, and that basically blew right over the Adirondacks here in northern New York, and that produced a huge acid rain problem up there. Now, what has happened since then is we've had these pollution controls that have come into effect, and so the acid rain issue not as big of a deal now in the Adirondacks as it was, again, maybe 30, 40 years ago when I was younger, back in the 80s and 90s, 1980s, 1990s. So again, bravo to us. We realized it. We helped clean it up. But in other parts of the world, obviously, this is still a major problem. So what are we looking here? These are, again, your current problem areas are in red. Yellow is potential problems because of air pollution, and green would be because of central sensitive soil. So again, still a problem here across the East Coast, but not as bad as it was. You'll notice here in Northern Europe, right, again, industrialized areas are producing this smog that then produces the acid rain. You'll notice here is the Shanghai, Beijing area of Eastern China, right? So again, here are areas where acid deposition is still a problem out there. And again, the solution is basically to put less of the less of those polluting chemicals right into our atmosphere. So harmful effects of acid deposition, again, contributes to respiratory disorders, releases toxic metals from soil and rocks, and it can bioaccumulate in fish that then weed or higher animals on the trophic level eat. Lowers the pH in aquatic systems. We spoke about that. Leaches soil nutrients, damages forests, and like I showed you, damages statues and buildings as well. So how can we reduce acid rain? Well, prevention is always less costly than cleanup. We've been finding that out over and over again in this course. Using renewable energy sources obviously reduces the impact of acid rain because you're not putting those chemicals into the atmosphere that then combine with other chemicals to produce the secondary pollutants of sulfuric acid and things like that, which produce the acid rain. All right, I'm going to leave you. This will be the final slide of lecture part one here of this lecture. One of our favorite charts: acid deposition, right? Prevention, reduce coal use, burn only low sulfur coal. Use natural gas and renewable energy where you can. Remove the sulfur dioxide, the nitrates from the smokestack gases before they actually get out into the air, and tax those emissions as well, right? Clean up, got to add lime to neutralize acidified lakes. You need to add phosphate fertilizer to neutralize acidified lakes. So just ways that you can kind of neutralize or bring that pH back up a little bit. And again, adding lime to neutralize acidified soils, also a way to clean it up. But again, much more expensive than preventing it in the first place. All right, that concludes part one of my lecture on chapter 19. Air pollution and ozone depletion. And as always, I thank you for listening.